So our second speaker of this afternoon is Giovanni Panti, who will speak about continued fractions, duality, and limit sets. Over to you, Giovanni.
Okay, thanks a lot. Thank you everybody for attending. I'm trying to convey a few ideas I've been thinking about in the last, say, couple of years about continued fractions and their relations with limit sets of IFS. Of course, the topic is not new. And let me just sketch the very classical formalism just to fix ideas. So all of you know that every irrational number in the, say, real unit interval x has a unique expansion in continued fractions with digits the positive integers. And moreover, the expansion is given by the action of the Gauss map that you see here to your left. That's the map x gets to 1 over x minus the floor of 1 over x. And now, given your starting point x, just apply the map and take note of the indices of the intervals to which the orbit belongs from time to time. So the first interval is 1. That's 2, this is 3, etc. So the symbolic orbit with respect to this partition is just this sequence of guys here. Now, if you fix, say, for example, a subset of the positive integers, for example, just a finite set, say 1, 3, 4, and you ask about the set of all points with expansion has digits included from the set only, then, well, the connection with IFS is clear because you look at the first, third, and fourth branch, you invert them, so you have the inverse branches here, and those are given by matrices, by 2 matrices, namely this guy here, corresponding to this, the projective action of this guy is just this branch, again acting on 0, 1, and now you have this guy here and this guy here. So you have a projective IFS whose limit set is precisely the set you were interested in. Now, that's no reason why you should restrict yourself to the classical Gauss map. There are very many possibilities around. For example, again, acting on 0, 1, you might consider x goes to minus 1 over x plus, now you take the ceiling instead of the floor. Or for an even more exotic example, you might take the map here to your right, and that is x goes to the absolute value of 1 over x. And now you subtract either the floor or the ceiling according to which of the two is an odd number. This is somehow weird, but the map is nice and has good properties. You might also ask about multi-dimensional versions of continued fractions. For example, the so-called Jacobi-Perron map acting on the unit square. That's the map xy goes to y over x in fractional part and 1 over x again in fractional part. Or, in order to make the role of matrices more transparent, maybe it is even better to take as a base space, for example, the unit simplex with vertices 1, 0, 0, 0, 1, 0, and 0, 0, 1. Then you split it into, say, 2 parts. At this point here, that's the point, say, 1, 1, 0. And then you have now 2 subsimplexes and 2 maps given by matrices. The first one, let's call it A naught, is, well, for example, you might take 1, 0, 0, 0, 0, Z, 0, 0, 1, 1, 1, 0. And this is going to contract the full simplex into the left-hand subsimplex. And you have an analogous map contracting on the right hand. So again, you have an IFS and the inverses of those matrices acting in the standard way. So you pick a point, you look at the subsimplex in which the point is, and you apply the corresponding inverse matrix. And the formalism is the same. You have an expanding map on the simplex, and you follow the orbit. You have an expansion now with 2 digits, and you may ask questions about lots of properties about the expansion. Now, which is my goal? Well, essentially, I have a foundational goal. I would like to know what is essentially a continued fraction. What's the reason of this question? Well, there are so very many piecewise projective maps around, but not all of them qualify to being a good Gauss map. We need good properties, both from the arithmetic and from the geometric point of view. For example, from the arithmetic point of view, we would like to be able to characterize the eventually periodic points. Dimension 1, this is the content of the Lagrange theorem and the Galois theorem from purely periodic orbits. Or to have, to have good geometric properties, so there should be some good relation with flows in homogeneous spaces. For example, hyperbolic two-dimensional manifolds, again, in the one-dimensional case. So our goal is to formulate certain conditions that have to be duality invariant, in a sense that I will make precisely shortly, on a projective IFS. Projective means induced by matrices, and at a later stage, this IFS will be even a graph-directed one, such that both the matrices in A to the minus 1, so the inverse matrices in A, and at the same time those in A, both of them define a good map. So we are not interested in just one map, but actually in a pair of maps, for reasons that we will see presently, acting dually. So let's simplify first. First simplification, just take my word for it, we might restrict to maps with finitely many branches. This is because there's a very well-known procedure called acceleration that recovers lots and lots of interesting maps by accelerating maps with finitely many branches. For example, here, the light blue map, it has finitely many branches, and its acceleration is the red map here, which is precisely the map I showed you before, a couple of slides before. And then in dimension 1, it is wise to replace the unit interval with this interval, the interval of positive reals. This is irrelevant because we are still working inside the projective line, but has the advantage that now we have a very natural semigroup of matrices acting on this guy, and that's precisely the semigroup, let's call it sigma, of non-negative matrices inside GL2Z. And let's take even a final simplification. We'll restrict to full Markov maps. This is because the problems are more transparent in this restricted setting, and also the solution can be understood more clearly. So we temporarily restrict to maps, let's call them F, from the positive reals to themselves, that result from partitioning zero infinity into finitely many unimodular intervals. By unimodular, I mean intervals with rational endpoints, say PQ and P prime over Q prime, such that if you form the 2x2 matrix with entries, those for numbers, the determinant has to be either 1 or -1. So here, for example, we have 4 intervals, 4 sub-intervals. This is 0, this is infinity, this is 1, and we have a further splitting at 1/2 and 1/3 here. Maybe you will recognize the familiar Faraday splitting. And this is the AFS, the contraction from the vertical 0 infinity to the horizontal one. And it is better to think in terms of hyperbolic geometry. So this is the model of that's the Poincaré disk. model of the hyperbolic plane. 0 is here, infinity is here, and the Fourier splitting is here. So this is 1, 1/2, and 1/3. And the action of the expanding map from this subinterval to 0 infinity, that's just the action of this inverse matrix, will expand this subinterval to the whole, expansion in the weak sense, because that's a parabolic fixed point. Or equivalently, it will map this oriented geodesic from 1 to infinity to the base oriented geodesic from 0 to infinity. And the same for the other 3 intervals. One thing that it is important to keep in mind is that this expanding action on the respective intervals becomes a contractive action on the negative reals. So each of those 4 inverse matrices will act contractively in the negative reals, forming an IFS, a contracting one here, that I will call the dual IFS. Now, for various reasons, for example, in order to characterize the periodic orbits, that's the content of the Lagrange theorem I was referring to before, or, for example, to compute the only absolutely continuous invariant measure for the map F, or for other reasons, even more reasons. It is quite important to understand a set of all admissible past of points in the domain of F. What do I mean by admissible past? Well, what is the future? The future is a point in the domain, so it is a point to which F can be applied as many times as you wish. To be even more precise, such that at each time step, precisely one matrix in a to the minus 1 can be applied. And I'm putting precisely 1 in quotation marks because, well, the overlaps do intersect, but the intersections are negligible. They are just at vertices. So essentially, up to sets of 0 Lebesgue measure, the map F given by those inverse matrices is well defined. So this is a point in the future, and well, dually, the point in the past must be a point which at each time step, precisely 1 with the same proviso, matrix now in A as opposed to a to the minus 1 can be applied. So it is a point in the limit set of a to the minus 1. And as I said before, since this guy acts contractively here in the negative reals, the past lives naturally here in the negative reals. Very well, and we have a pair of bonus forms. Well, the first bonus is that the volume form, the hyperbolic volume form, is automatically preserved by this two-dimensional map. That's the map that maps a pair xy, where x is the future and y is the past, component-wise, using the inverse of the matrix indexed by the interval in which x lies. This actually is a map not on points but on geodesics, because if you identify a pair xy with a geodesic, that precisely the geodesic started from y, which is the past, and traveling towards sx, which is the future, then that action is precisely, well, we'll map this geodesic to another geodesic. And so that guy here, that maybe people will recognize to be the so-called natural extension of the original map F, is actually a map on the space of geodesics, which is the so-called de Sitter space. And we have a second bonus, that if we conjugate the any acting inverse matrix with this matrix here, that hyperbolically is just the rotation of pi about the center of the disk. So it is we are swapping the future and the past. Then this matrix magically gets converted into its transpose. So we might as well take as dual IFS not a to the minus 1 acting on the negative reals, but A transpose acting on the positive ones. This is just cosmetics, of course, but it is nice cosmetics because the transposition operator is an anti-orthomorphism of our central player, remember, the semigroup sigma of non-negative matrices in GL2Z. Okay, everything was fine and good up to now, but now there are problems. And the key problem is that this operation of taking transpose transforms trivial IFS, such as this one. This is A, the one this guy here, given by the inverses of those four branches. And this is definitely a trivial IFS because the attractor is just zero infinity. There's no discussion about that. Into definitely non-trivial ones. This is A transpose given by the transpose of those four matrices acting again on zero infinity, but now we have gaps and moreover overlaps. So in order to understand which is the limit set of this guy, well, we need a bit of work. And this work is necessary because it is essential that we have a good attractor. What do I mean by being a good attractor? I mean, first, that it has to have non-empty interior, because otherwise there would be no connection whatsoever with a good geodesic flow, at least over good hyperbolic surfaces. Because we are interested, for example, in interpreting the expansion in continued fractions as codings of return times to a section of the geodesic flow. So this condition is for sure necessary, and it is also necessary that in both cases, the trivial one, but the non-trivial one, this guy here, the images of the attractor under the elements of the respective IFS do not intersect too much, because otherwise we could not define the pair of dual maps we were interested in. So this is the problem, and it is a fortunate fact that both requirements actually can be met in this setting of full Markov maps. This is not completely trivial. It requires a proof. Well, and since every talk should have a proof, this is my proof. The proof is obtained using several ingredients, the first one being algebra. So remember, we had this semigroup of non-negative matrices, and it is a good fact that this semigroup has a nice algebraic structure. It is generated by three matrices, this guy here, and this guy here. And moreover, they generate it almost freely. I mean by almost freely the following fact, that there are precisely three relations, three identities among those matrices, these three identities here, and every other identity can be algebraically deduced by those three guys. So it is definitely a good semigroup. And moreover, this is precisely the algebraic structure of another semigroup of now affine self-maps acting on 0, 1. So we have 0, 1 here, as opposed to 0, infinity here. And those free maps are, of course, this linear map here, this linear map here, and F is the flip exchanging 1 with 0. So that's the semigroup of all affine self-maps on 0, 1 with dyadic coefficients. So coefficients which are rational numbers with the power of 2 in the denominator. Well, so we have an algebraic isomorphism, but more than that, this algebraic isomorphism is actually induced by conjugation, by the so-called Minkowski question mark function. That's the function introduced by Minkowski more than 1 century ago. That's a homeomorphism from 0, infinity to 0, 1. And it is computed in this way. Given x, which is here, you compute this number, you expand it in continued fractions, and then you compute this alternating series that involves those entries. And this series converges to a number, m of x, And this is a homeomorphism that that conjugates the action of L to the action of here, to the action of capital L here, and the same for N and for F. And moreover, a composition of maps is preserved so that it globally conjugates every element in the semigroup with the corresponding linearized one, and in particular linearizes every IFS on 0 infinity to a linear one on 0 1. So it is really universal. It simultaneously conjugates everything. Of course, well, the bad guy here, so a transpose, gets linearized, and it is now a transpose lin for linear. It is still a problematic one because still we have gaps and still we have overlaps, but at least is linear. So since it is linear, we can apply something in the literature. Which are the ingredients, the final ingredients? Well, first of all, the maps in A, the original IFS, generate a free subsemigroup. This follows from the ping-pong lemma. And moreover, once linearized by the Minkowski function, the sum of the contraction rates is 1. Both properties go through to the dual one. And that's a good fact. Now, by results, classical ones, by Bandengraf, the attractor of the linearized IFS, let's call it K-lin, has a positive Hausdorff measure in its similarity dimension. Here the similarity dimension is 1, so just this means a positive Lebesgue measure. By results by Schiff, the linearized IFS satisfies the strong open set condition with respect to an open set, let's call it V-lin, whose closure equals the linearized attractor. Actually, we might take the interior of the attractor for V. In particular, this guy here has non-empty interior, and since the Minkowski function is a homeomorphism, this property immediately transports to the real world K, that's the attractor, the M counter image of the linear one. So at least we obtain our first goal, that the attractor is not small. And what about the second goal? The second goal, remember, was that its images should not overlap in large sets. Well, this is surely true in the linearized case for the very good reason that the similarity dimension is 1, and since the images are disjoint, of course. But now we cannot transfer this fact immediately to the projective world, just because the Minkowski function is singular, so its inverse is singular as well, and well, it might well transform set of 0 measure to sets of positive Lebesgue measure. So the corresponding statement for the dual limits for the dual IFS is not automatic. However, it is still true. The proof is more involved. I am not entering into this. It goes through results of those people, and the key ingredient is the divergence of this Poincaré series, that it is indexed differently from the usual, not by the semigroup not by the group generated by A, but by the semigroup. So everything works, and we obtained what we wanted, at least remember in the simplified setting of full Markov maps. Now, this setting is too restricted. It's too restricted because, well, first of all, because it is restricted, and second, because the two roles of F and of its dual are asymmetric. We do not want that. We want to be able to treat cases such as this one. Remember, that was the slow map whose acceleration give the weird map. And this kind of maps really intrinsically cannot be treated in the setting of ordinary IFS. Look at this guy here. This is the contracting matrix that will contract this segment into this segment. If you compute, the trace is 1. This means that this matrix is elliptic. It is conjugated to an hyperbolic rotation about some point. So in particular, if you take any proper subinterval of the projective line, it will never, not necessarily unimodular, it will never act contractively on any given proper subinterval. So intrinsically, it is not possible to treat those kind of guys using the standard formalism of IFS. But fortunately, both issues can be treated with the same solution. The same solution is to replace ordinary IFS with graph-directed ones. So this guy here is expressed by this graph. Now we have two nodes corresponding to the two subintervals, 0, 1, and -1, 0, both of them being unimodular. And this problematic guy here corresponds not to a map from an interval to itself, but from a map to an interval to the other interval, from here to here. In the graph-directed formalism, arrows go in the opposite direction, so you see the weird direction of arrows, and everything works. Well, of course, there are technicalities all around. These are treated in this a couple of papers. But the end picture is, in my opinion, satisfying because it divides. Of course, we are still working in the one-dimensional case. We are separating the abstract setting from its geometric realization in the following sense. I'm defining an abstract continued fraction to be a graph-directed iterated function system whose nodes are indexed by disjoint copies of the universal unimodular interval 0 infinity, and whose edges are matrices in sigma, subject to the following two conditions, which are intrinsically duality invariant. First condition is that the edges should generate a free sub-semigroupoid. It is not a semigroup because composition of matrices is not everywhere defined. It is defined only according to the graph-directed structure. And the second condition, well, you remember that we had a condition on the sum of the linearized contraction rates that had to be 1 in the one interval setting. Here, in the generalized setting, we form a certain matrix reflecting the incidence, and the entries are sums of linearized contraction rates, and the condition becomes 1 on the spectral radius of that matrix. Essentially, the second condition ensures that the attractor is large, and the first one ensures that there's not too much overlapping. And those two conditions are essentially intrinsically duality invariant, where by duality we mean swapping the direction of all arrows in the graph, and at the same time swapping every matrix with its own transpose. So this abstract guy, well, we have to interpret it in geometrically. What do I mean by a geometric realization of this abstract guy? Well, I mean the choices of actual unimodular intervals in the projective line that will take the place of the universal one here. And the condition is that both the attractor and the dual attractor have null overlappings. Now, not every abstract continued fraction in this sense has a geometric realization. They may or they may not. But the good news are that if they have, whenever such a realization exists, then all good properties of continued fractions, such as Lagrange-Galois theorem, all the relations with the geodesic flow, the realization of the natural extension as a section of that geodesic flow, etc., everything holds. So the picture is, in my opinion, nice because it splits the abstract part from its geometric realizations. Well, of course, now there's the problem, and the problem is that the n-dimensional case. The n-dimensional case is quite problematic and very interesting. So let's concentrate on n equal 2 to make things clearer.
Giovanni, just to let you know, it's half past, so if you could just wrap up in the next couple of minutes.
I will be very quick. So what can we surely do? We can surely replace zero infinity with copies of the standard one-dimensional simplex, no problem. And there's no problem even to replace sigma with the semigroup of non-negative matrices in GL, well, say 3Z. No problem about asking that the edges of a graph-directed IFS that we want to test for goodness generate a free sub-semigroupoid, no problem. And the transposition retains a geometrical meaning. But however, there are serious issues. The first issue is that now sigma is algebraically just horrible. It is not finitely generated anymore, and there's no possibility of listing down all relations. It is not true that decreasing sequences of unimodular simplexes as opposed to intervals necessarily shrink to a point. So even the classical projection maps of IFS from paths in the graph to delta may not be well defined, just because if you are shrinking to say a segment instead to a point, how do you define pi? And moreover, there's no canonical relation with similarities, nor a unique Minkowski function. We can linearize in very specific cases, such as these classical cases, but forming an ad hoc Minkowski function. But this function is going to change from map to map, and for sure it will not uniformly linearize every map here in sigma. So the end result is that attractors are definitely quite mysterious. There are very simple and harmless looking maps whose dual attractor have empty interior. These are algorithms of expansion which are geometrically very bad. They have no relation whatsoever with hyperbolic or homogeneous spaces. So the main problem that really is a problem, given a graph-directed IFS in higher dimensional case, formulate appropriate conditions, duality invariant ones, to ensure that both the attractor and the dual one, well, have non-empty interior and negligible overlaps. If you look at simulation, you get pictures like this in several cases, and it is completely problematic to understand the largeness or not of those attractors, and moreover to understand the overlapping of those guys under the various maps. Well, okay, I'm sorry for the delay, and thank you very much for your attention.